Hello and welcome to our lesson on arithmetic and geometric sequences. So a sequence or a mathematical sequence is just an ordered list of numbers, and it's possible that that list of numbers follows a pattern, but it may or may not. So our mathematical sequence may or may not follow a pattern. And you've already had an assignment where you got to look at a few sequences and try to find some patterns, whether they were lists of numbers or figures, where within the figures you could make lists of numbers. But let's take a look at a few more lists, and then I'm going to talk about a specific type of sequence. Again, arithmetic and geometric will be the focus. So let's take a look at the sequences that are in this box here and see if we can't find the pattern. So in the first sequence, when I'm looking for a pattern, the easiest thing is there some number that I'm adding continually? Is there some number that I'm subtracting continually, or multiplying or dividing? The four basic operations are the easiest ones to look for. So with this first example, to get from 2 to 6, I'm adding 4, and then if I continue that, I continue to get to the next terms. So 6 plus 4 makes 10, 10 plus 4 makes 14, and so on. So in this first list, I can see my pattern is to just add 4 to get from one term to the next. In the second list, if I do the same thing, to get from 3 to 6, I'd have to add 3, but then to get from 6 to 12, adding 3 doesn't work, so I'm going to get rid of that option, and I don't know what just happened with the pen there. And then adding didn't work, obviously not subtracting because we're getting larger, so let me try multiplying. To go from 3 to 6, I could multiply by 2. 6 to 12, I could multiply by 2. 12 to 24, I could multiply by 2. And so that works. So I can see now in this second list, my pattern is to multiply by 2. Now if I look at the next list of numbers, I don't know that I can see a pattern. So adding or subtracting, in this case I would subtract 2, but then here I would add 3, and then here I would subtract 3, and then here I would add 4. I don't really see a pattern in those numbers. Let's see. Here I would add 4. So we've got positives and negatives here. Yeah, I can't really see a pattern that way. Multiplying or dividing, I would have to divide by 3 to get from 3 to 1, but then multiply by 4, and then divide by 4, and then multiply by 5, and then multiply by some decimal. So I don't think there is a pattern that I can see. Actually, those numbers look like the digits of pi, but I don't see a pattern in here. So I'm just going to say no pattern exists, at least no pattern that I can find. And that would be true for anything that you're going to be working on as well. We should be looking for a basic add, subtract, multiply, divide sort of pattern in there. All right, so let's look at the next list. If I'm adding, I'd add 1 here. To get from 6 to 8, I would add 2. 8 to 11, I'd add 3. 11 to 15, I would add 4. So there's another adding pattern in this one, but I'm adding 1, then 2, then 3, then 4. So I would assume next I would add 5. So I could describe this pattern as adding consecutive numbers being one right after another. So I'm going to add consecutive numbers, and I want to say starting with 1 because I don't want those consecutive numbers to just begin anywhere. So I'm adding consecutive numbers, but specifically starting with 1. All right, let's look at the next one. Since we're getting smaller here, I'm going to try by trying to subtract 3 minus 5 would take me to negative 2. Negative 2 minus 5 would take me to negative 7. Negative 7 minus 5 would be negative 12. So that's a pretty clear one here. I'm subtracting 5 to get from one term to the next. In the next one, numbers are getting smaller, but the differences are not the same. So I'm going to guess this is a divide problem. Now I can see from here to here that I would be dividing by 4. Let's see if that works all the way through. Pull out my handy Desmos calculator. If I take 256 and divide it by 4, I do get 64. So I divide 4 here. If I take 64 and then divide by 4, I get to 16. And obviously 16 divided by 4 is 4 again. So that's a nice pattern. We are dividing by 4. In the next list, let's see, I'm not adding to get from 1 to 1, maybe multiplying. Multiplying by 1, and then here I'm multiplying by 2, and then 2 times 3 would get me 6, and then 6 times 4 would get me 24. So this is another multiply one, but I'm multiplying by consecutive numbers. So multiply consecutive numbers. Again, I want to say that I'm starting with 1. And I'm getting really sloppy here. Apologies for that. And then I got one more on the list here where it looks like, let's see, we've got 2 and then 1 over 2, 3 and then 1 over 3. So I would maybe guess that I could go 4 and then 1 over 4 and then 5 and then 1 over 5. Looks like this is a list of consecutive numbers and their reciprocals. So 2 then 1 over 2 would be the reciprocal of 2, 3 and then 1 over 3 would be the reciprocal of 3. So this is consecutive numbers followed by their reciprocals. And we're starting this list at the number 2. So consecutive numbers followed by their reciprocals, starting, oops, can't spell, starting with 2. Okay, so now that we've established some lists and some patterns, or maybe not a pattern here, I want to focus on 2 specific types of patterns that we see here in what we call arithmetic and geometric sequences. So if a series is, or series, excuse me, if a sequence is what we call an arithmetic sequence, it means that it's formed by adding. So an arithmetic sequence is formed by adding. Now, we've got several examples in this list where we're adding. We're adding 4 here, we're adding consecutive numbers here, and then actually subtracting is like adding a negative, so we're doing that here. However, only 2 of those are actually arithmetic. So when we're adding, we want to be adding a fixed amount. So when we add a fixed amount, which we call the common difference between our terms, then that's what we call an arithmetic sequence. So the common difference we're going to call D. That's the number, the fixed amount that we're adding to get from one term to the next. So this would be an example here that is arithmetic. And technically, we would say that this arithmetic sequence has a common difference of 4. That's the fixed number that we added to get from one term to the next. Okay, so that's what we call arithmetic. The example here is another one. This one on the list where we were subtracting 5. This is another example of an arithmetic sequence. Because when we're subtracting 5, that's the same as adding a negative 5. So we would say that the common difference between these terms is negative 5. Now, in this other one we were adding consecutive numbers, remember we were adding 1, and then we added 2, and then we added 3. That's not a fixed amount that we add every time, so even though it's an adding pattern, this is not arithmetic. Okay, so I'm just going to leave that one blank for a minute. All right, now if it's the other type we want to focus on today, which is called a geometric sequence, then we have a different type of pattern. The pattern is formed by multiplying. Okay, by multiplying by, again, a fixed number to get from one term to the next. And that fixed number we're going to call the common ratio between the terms, and we're going to use the letter R. So we've got a few multiply ones here and a divide one to look at. So we're multiplying by a fixed number on this first example for geometric, multiplying by 2 every single time. So we would say that this is geometric, and that the common ratio between the terms is that fixed 2. We're calling it a common ratio because a ratio is a fraction. If you make a fraction of any 2 terms, so 6 divided by 3, we get 2. 24 divided by 12, we get 2. 12 divided by 6, we get 2. That ratio is common throughout the consecutive terms. Okay. Now, if we look at another multiply example down here, we are multiplying but not by a fixed amount. We multiplied by 1, then by 2, then by 3, so since that ratio changes, we're not going to call that geometric. But here, where we're dividing by 4, that's the same as multiplying by 4. So we're going to say that this is another example that is geometric, and the common ratio between these terms would be 1/4. So let's maybe make a note here. Subtract 5. This is the same as add a -5. And then here where we have this divide by 4, that's the same as multiply, oops, not mut, but mult by 1/4. Okay. And then we've got another multiply example down here, but again, we're sorry. Oh, we talked about this one, I think, already. Okay, multiplying by consecutive numbers. So again, that ratio changes. Now, the others that have patterns are sequences, just not arithmetic or geometric. So no pattern exists on this one. We wouldn't be able to classify it as either arithmetic or geometric, so we'll go ahead and say neither because there's no pattern here. Again, this isn't arithmetic or geometric, so we'll say neither here. Same for this one, and again for this last one. Okay, so hopefully that concept makes sense. And now we're going to do a focus on the arithmetic and geometric sequences themselves. So if our sequence is arithmetic or geometric, if we're adding a common difference or multiplying a common ratio to get from one term to the next, then we're able to write what we call an explicit formula for the general term of that sequence. So for example, for geometric, again, if it's geometric, we're going to be able to write what we call an explicit formula for the general term of that sequence, which means we can write a formula that can be used to calculate any term in the sequence. So for example, if I went back to, let's say, this list here, and I wanted to find the fifth term, it wouldn't be that hard to continue the pattern and find the fifth term. But if I wanted to find, let's say, the 100th term, I don't want to continually add 4, dozens and dozens and dozens of times in order to figure out what that 100th term is. And that's where the explicit formula would come in handy. So here's how it looks for a geometric sequence. This is notation for what we call the general term. So this piece of the formula, this is called the general term or the nth term of the sequence. So if n was replaced by some number, so for example, if it said like a sub 5, that would be the fifth term, a sub 10 would be the 10th term. If it's a sub n, that's the nth term of the sequence. So this is a general term. In general, any term of our sequence can be found by doing what this formula says to do. It says take a sub 1, which is notation for the first term of the list, multiply it, that's what the parentheses tell us to do, by r, which we've already stated is our common ratio. And then we're going to raise that to a power, and this is a power here, so this is r to the n minus 1 power, and that power, again, n minus 1 is going to be the term number minus 1, so n is the term number. Okay, so if I just wanted to write an explicit formula for a particular sequence, then I'm simply going to input two things. I'm going to input my first term and my common ratio, and then I have an explicit formula for a specific sequence. Now, if I actually want to use that explicit formula to calculate a term in the sequence, then I'm also going to replace n with the term that I'm looking for. Okay, so let's try this out. Hopefully you're not feeling overwhelmed by formulas and math. Let's take a look. So for example, in this first one, I want to write the explicit formula for this sequence. Now, we're going to be looking at formulas for arithmetic and geometric, so we want to make sure that we're using the right formulas. I know this is in the geometric section here, so I know it's a geometric list, but I still want to verify that I'm multiplying by some fixed number to get from one term to the next. And it looks here like I'm multiplying by 3, and then I'm multiplying by 3 again, and then I'm multiplying by 3 again. And if it was not easy for you to see, remember the ratio comes from, if I can't tell what I'm multiplying by to go from here to here, I can work backwards using division. If I make a ratio, a fraction of any two terms, I should be able to figure out what that ratio is going to be. So I could take my second term, negative 18, and divide it by my first term, negative 6, and get that common ratio every single time. maybe that would be helpful to note up here. If you want to find r, because you can't necessarily see it, maybe arithmetic's a little rusty, you can always take your second term, which we'll call a sub 2, and divide it by your first term, which is a sub 1. Okay? So, again, this is going to be geometric. I know that my common ratio is going to be 3, and I can see from my list here that my first number, my first term, is a sub 1. So my formula for this particular sequence would say the general term, the nth term, is that first term multiplied by that common ratio raised to the n minus 1 power. And so that's a formula I could use to generate any term on the list. Now, if I wanted to verify the formula was correct, then I can actually plug numbers in and make sure that it produces this list. So if I plug a 1 in for n, it should give me, if I plugged a 1 in for n, it should give me the first number on the list. If I plugged a 2 in for n, it should give me the second number. Plug a 3 in, I get the third number, and so on. So let me show you how that looks, just to verify my work. If I have negative 6 multiplied by 3, and I raise it to a power, it's n minus 1, so I'm going to plug in, I want to find the first number, I'm going to put 1 minus 1 there, I get negative 6, the first number on the list. If I plug a 2 in, I get negative 18, the second number on the list. Plug a 3 in, I get the third number, plug a 4 in, I get the fourth number, and so on. So there is my explicit formula for this particular list. Okay? In number 2, we're asked to find the general term of a sequence, which is different directions but asking for the same thing. The explicit formula is a formula to find the general term, the nth term. So again, I want to make sure this is geometric so that I'm using the right formulas. I am dividing by 10 to get from here to here, again here to here, again here to here. If I'm dividing by 10, then I am multiplying by 1/10. And if you're not sure about that, again, take your second term and divide it by your first term, and you get 0.1. If you notice in Desmos in the blue there's a little button where you can change from a fraction to a decimal. So I can go back and forth. I prefer the fraction version, but decimal would be fine too. So you get 0.1 or 1/10 for that common ratio. And again, 300 here is our first term. So a general term for this sequence, a sub n, the nth term, would be that first term, 300, multiplied by the common ratio, 1/10, or 0.1, raised to the n minus 1 power. So there's your formula for that sequence. And now we're going to just take this a step further. Let's actually use our formula to calculate a term in the sequence. So for example, here on number 3, we were asked to find the 15th term of this sequence. And I can see in this sequence I am multiplying by negative 6 to get from one term to the next. And so this is geometric. There is a common ratio of negative 6. My first term is 1. So I would say that any term on this list, the general term, a sub n, or the nth term, would be 1 times negative 6 to the n minus 1 power. Now, this one asks me specifically to find the 15th term. So now that I have my formula, I'm going to plug 15 in to do that. So a sub 15, that 15th term, is 1 times negative 6 to the 15 minus 1 power. And then I'm just going to go into my calculator with that expression, and I'll have a sub 15 equal to, this is notation here, so that's just going to stay a sub 15, but I want to figure out what is 1, let me make this keyboard a little bigger, what is 1 times our negative 6 raised to the 15 minus 1 power, and I'm just going to, maybe, I don't hope that you caught what I did, to make an exponent using that a to the b button. Instead of typing in 15 minus 1, you got to be careful here. If you type in 15 minus 1, it drops the 15, or the 1 out of the exponent. So if you want to keep the 15 minus 1 all together in the exponent as it should be, you're going to have to put it in parentheses, which is just more work than I would like to do, and so I would just take 15 minus 1, call it 14. But it gives me this really ugly number, and we have to be able to deal with this ugly number. So what it says, I can't copy this, is we have 7.8364164096 times 10 to the 10th power. This is scientific notation. This 10 to the 10th power, I don't know if the calculator will tell me what this is. Yeah, it just it gives me scientific notation again. Um, it's a 1 with a lot of zeros, 10 zeros in fact. And so if you're multiplying like 10 squared, right? 10 squared is 100, so that's a 1 with 2 zeros. If you multiply a number by 100, it moves a decimal twice. If you multiply it by 1,000, it moves it 3 times. If you multiply it by 10,000, it moves 4 times. So 10 to the 10th power is telling us the decimal should be moving 10 times on this number. So move the decimal 10 places to the right to make this number bigger. If that was a negative 10, we'd make it smaller. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is silly, makes the decimal land there, which means our 15th number is actually going to be 7, 8, 3, 6, 4, 1, 6, without all the decimal. 4, 0, 9, 3. Now let me put some commas in so I can try to read this. So 78,364,164,093. That's the 15th number on this list. Gigantic number. And hopefully it makes sense that that number is so unreasonably large because we have this list that we're continuing to multiply by 6 to get from one number to the next. We do that 15 times, the number starts to grow really fast. That's what we call exponential growth, if you remember anything from your algebra days. Okay? All right, let's look at one more. Where it says find a sub 12, that means the 12th term. They're telling us where our list starts, and then we're multiplying by 0.25. So instead of multiplying by, in this last one, by 6 and making those numbers get bigger, we're multiplying by 0.25, which is 1/4. That's dividing by 4. Our number should be getting smaller. So let's write our formula first. The general term on this list, again, is that first term multiplied by the common ratio raised to the n minus 1 power. We want to find the 12th term, so a sub 12 would be negative 4,096 times 0.25 to the 12 minus 1 power. And then again, I'm just going to go to my calculator with that. So I have negative 4,096 multiplied by 0.25. I'm going to raise that to the 12 minus 1 is the 11th power. And I get an ugly decimal, which I don't want to round. And you can write that decimal answer, but if I have the option to make it a fraction and the fraction is nicer to write, then I'll take that option. So yeah, this is a much nicer answer, in my opinion. So I'm going to make the fraction answer. Okay? If you wanted to write the decimal, again, the decimal would be fine. Alright, so there's a snapshot of the geometric sequences. Now let's do something similar with the arithmetic. We've got a different formula, obviously, for a different rule. This is what the explicit formula for the general term of an arithmetic sequence looks like. The arithmetic, remember, is where we're adding to get from one term to the next, adding a common difference. And so again, this is still notation for the general term or nth term. General term or nth term on the list. A sub 1, again, in our formula, represents the first term. This time, instead of a common ratio, we have a common difference. So there's our common difference. And again, we have n in our formula, which still represents our term number. Okay, so just like with the other one, it's a different formula, but it's a similar concept. If I want to write an explicit formula for a particular sequence, I'm inputting two things. I'm going to input the first number on the list, and in this case, the common difference. And then if I want to actually use this formula to find a specific term number, then I'm also going to plug in n. Alright, so let's try to write the explicit formula for this list. Again, you're going to have different examples. Make sure you're using the right formula. Let's make sure this is arithmetic. So I'm adding a constant 5 to get from one term to the next here. So this is arithmetic with a common difference of 5. Here's my first term. So formula says the general term is a sub 1 plus the common difference multiplied by n minus 1. This would be an acceptable form of the answer, although it can be simplified, and I would prefer the simplified version. But this is one version of the formula, so you could say this is the explicit formula. Or you could simplify. If we were to simplify, then we're going to distribute the 5 here. So if I distributed that 5 times n would be 5n, and 5 times negative 5 would be negative 5. And then we would have two like terms that we could combine. If I put together that 3 and that negative 5, then I have a sub n equal to a 5n, and then again the 3 and the minus 5 go together to make a minus 2. So this is another version of the formula. Either answer would be correct. One's in simplified form, one's not, but either would be totally fine. Same thing then for number 6. Directions are different, but it says find the general term, which means write the explicit formula for that nth term or general term. So again, we're going to say a sub n is, get ahead of myself. Well, let's make sure it's arithmetic. Looks like I'm subtracting 4 here, subtracting 4 again, and that pattern continues. So our first term is 27, and then our common difference is minus 4. So the general term here is going to be our first term plus our common difference, so let's go minus 4 times n minus 1. Again, a perfectly acceptable version of the formula for the general term. Or if we were to simplify, we've got 27, negative 4 times n, and negative 4 times negative 1 would be negative 4n plus 4. And when we combine those like terms, we have a negative 4n, 4n, and 27 makes 31, so plus a 31 here. Again, either version, totally fine. Alright, now that we can write the formula, let's use it. If I, for example, on this next list wanted to find the 50th term, first, I can see that I am subtracting 4 to get from one number to the next. Sorry for the lack of variety there. So this is an arithmetic sequence where our common difference is negative 4. I don't want to keep subtracting negative 4 to find the 50th term, so I'm going to use my formula. So we start with a sub n equal to our first term, which is 12 minus our common difference of 4 here times n minus 1. And now I want to, in this case, find the 50th term. So I want to find a sub 50. So 12 minus 4 times 50 minus 1. And then just go to my calculator for the arithmetic. So I have 12 minus 4 times 50 minus 1 means that the 50th number on this list would be a negative 184. Alright, and then last one, which if you want to try would be a good place to pause the video and give it a shot. Otherwise, let's just knock this out. I'm looking for the 100th number on a list here. Well, list starts at 10, and then 6 is being added to continue that list. So the general term here would be 10 plus that difference of 6, n minus 1 times. If I want to find the 100th term, a sub 100, then I have 10 plus 6 times 100 minus 1, and I go to my calculator, and I got 10 plus 6, nope, careful, fat fingers, I don't know if you have that issue, but I do. I got 100 minus 1 in the parentheses. Alright, so 604 would be the 100th number on that list. Okay. Alright, so a little overview. Again, should be able to look at a list of numbers, identify a pattern. If the pattern is that we are adding a fixed number or multiplying a fixed number, that sequence is either arithmetic or geometric, then we're able to write these explicit formulas to find or for general terms and then use them to actually calculate terms on the list. Hopefully that's enough for you to get going on your assignment. If you have any questions, by all means reach out, let me know. Until next time, take care.